Today we're going to be talking about circuit diagrams and how and why we use them. And then we're also going to talk about how to put multiple resistors in a circuit. Specifically, they're all going to be in a row, and that's going to be a series circuit. So let's get started. And the first thing that we got right here is something that looks completely unrelated. So this is a map of London, specifically a map of London's tube system and all of the routes of all of the trains that are going throughout the greater London area. And we can look at this and go, well, it's possible to get from Croydon to Heathrow on this, but looking at this and looking at this map, I have no idea how I would do that other than there'd be an orange line and a blue line involved someplace. So, in order to make the London Underground a lot easier to use, they needed to make a much more useful map. And the map of the London Underground that we know today, along with every other subway map, was actually designed by an electrical engineer that used the same techniques that are used for circuit diagrams into how to show all these connections in a map. So rather than the map showing exactly where everything is and the exact route that all of the trains take underground, it doesn't really matter. What matters is, hey, look, it's going from this point to that point along the way. So there's a couple of other features on this map that are very helpful because it shows how things are connected. So we can get from Croydon on the orange line, then move to the gray line, then move to the yellow line, then move to the blue line, and then that'll take us all the way out to Heathrow. And now we can tell that because we know what train lines are connected at different stations and which ones aren't. Other things that we can tell from this is that we can take a look at the symbols that represent the various different underground stops and know what's connected to what and more about them. For instance, whether or not they're handicapped accessible, or whether or not you can transfer directly, or you have to go out and back in and then probably end up paying more money. So this is a very useful thing for showing how the subway works. And this is going to be similar for showing how our circuits are put together using this kind of a diagram. So I mentioned earlier that this will show you symbols for what the stations are doing. We're going to have something similar when it comes to the symbols for our circuit diagram. So this makes life a lot easier because it's going to be like reading a map rather than reading a diagram where everything is all twisted up together and it looks like a rat's nest. So we've got symbols for voltage sources, and there's lots of different symbols for voltage sources here, depending on exactly what the voltage source is, what it's doing, blah, 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 blah. But the only thing that we really care about in this diagram of all the various different symbols are the two in the middle. So that's going to be the symbol for a battery. And you might recall from chemistry class that the early batteries were voltage chemical piles, chemical cells, and that's essentially what this is drawing, is it's drawing different cells on top of each other. So that's going to be the symbol that we're going to use for a battery, and it's going to be lines on top of each other, or left and right. So you have big line, small line, big line, small line. And that's going to be the symbol that we're going to use for a battery, and that's going to be the voltage source that we're going to use. Resistors. So on the top, we've got a symbol or a drawing of what a resistor looks like with all the different color codes, but this is a royal pain in the neck to draw. What we've got in the middle is this jagged line, which is a much easier thing to draw, and that's going to be your standard symbol for a resistor. The box at the bottom you also sometimes see, but it's not what we're going to be using for the most part in this class. So we also have our measuring devices. And those are going to be circles, a big V in the middle of the circle that shows our voltmeter, which measures the voltage. That's the potential difference between point A and point B. And then we also have the ammeter, which measures the current in amps that are going through the circuit. So with that in mind, what we've got here is an example. So on the left, you see that we've got a nice, pretty circuit diagram that shows that we have a voltage source, in this case a battery. We have a voltmeter that's measuring the potential difference across the battery, and that's going to be 6 volts. We have an ammeter that's measuring the current flowing through the circuit, and we have a resistor. And over on the right-hand side, you see that we've got a mesh. So this is a somewhat similar setup in that it's got a voltmeter, it's got an ammeter, and it has a resistor. But you looking at this thing over on the right, it's difficult to see exactly what's going on because everything's all woven together. So this diagram on the left is a much easier way to see and interpret what's going on the right because what's going on the left shows the connections. All right, so now let's talk about putting multiple resistors in a series. So we're going to put multiple resistors in a circuit and we're going to wire them in series. So we now have a circuit that has multiple resistors. And I've got 3 resistors here, a 3 ohm, a 4 ohm, and a 5 ohm. So these are laughably small resistors, but they happen to make the math work out for the example that we're going to do, so we'll deal with these very low resistance resistors. All right, so we got these 3, and what we can see is if I switch screens to this one right here, we now have these 3 resistors in a circuit. So we have our voltmeter down here, and we have our 3 resistors, and we have our ammeter, all set up in a very, very similar way to what's shown in the circuit diagram. And if you were to wire this in real life rather than this virtual lab, you'd end up having wires going every which way, so the circuit diagram would be even more valuable. All right, so let's go back to where we were. All right, so we got that, and here they're wired in series, which means that the current must flow from one resistor into the next. So, and the current has no choice as to where to go. And we can see this if we turn this on in the simulation over on the other screen. So here we can see this if we turn on the current. So here we can see the electrons that are going around in a circle. And each electron is going from one resistor to the next, and then around through the ammeter, which is measuring the current going through it. And then it goes back to the battery. So the current is the same everywhere in this circuit because the electrons have no choice as to where to go. They must follow this one path. So let's head back to the slides, and here we go. Let's talk about how we're going to evaluate these circuits. So resistors are electrical components that for the most part are used to fine-tune the current that's passing through the other parts of your circuit. But anything that uses electrical power has a resistance, and this could be drawn as a resistor. And it certainly will be calculated as one. And this is why this is so important, because knowing how much power each component uses is necessary to make every single device, every single electric device that we use on a daily basis work. So to do this, we need to, in order to calculate that power, we need to calculate the current and the voltage going through each resistor. Now, when I learned how to do this, I basically was given the equations and said, go told to go solve it, and then there would be at the end a whole mishmash of equations written in the margins and all over the place, and finding exactly what I was doing where was always a disaster. So a much nicer way to solve these kinds of problems is to use a table like the one that we have here. So up at the top we have Ohm's law, V equals IR. And down the left-hand side, we have the various different resistors that we can use. So we have resistor A, resistor B, resistor C, and total. So let's take another look at our circuit and let's start filling some stuff in. So here is our circuit, and we're going to be filling in this table sort of like a Sudoku puzzle. So here's our table again, this time without cutting the L off. So let's go ahead and fill in all the things that we know. We know that we have our 3 resistors. So we have 3 ohms, 4 ohms, 5 ohms, and we know that the voltage is sitting there at 6 volts. So now, what's our next step? Our next step is to add up all the resistors. So when resistors are in series, they all resist one after another. And each resistance gets added together. So the resistance of resistor 1 gets added to the resistance of resistor 2, gets added to the resistance of resistor 3, gets added to the resistance of you get the idea. So you add up all of those, and that's going to give you the total resistance for the circuit. And we can bring this back, and we can see that 3, 4, 5, that all adds up to 12. And now what we have down here at the bottom is our total. We can now use Ohm's law to calculate what the current's going to be. The total current has to be 0.5 because V equals IR. The I is going to be the voltage divided by the resistance. 6 divided by 12 is going to be 0.5. Now, in the circuit, we know that the current doesn't have a choice as to where it's going to flow. So the current is going to be the same everywhere. So as soon as I know that this is a series circuit, hey, look, all the way up and down, the current's going to be the same throughout the whole thing. And you also might notice that somewhere along the line, I added an S to the upper left-hand corner of this table. And that's to remind me that what we're dealing with right now is a series circuit. Now from here, we've got Ohm's law, V equals IR. I have my current, I have my resistance. Now I can multiply the current and the resistance together, and that's going to give me the voltage. That's going to give me the potential difference across each resistor. So that's going to give me the voltage drop across each resistor. That's going to tell me the potential difference of the electron before it enters the resistor and right after it leaves the resistor. And that's what I can use to then calculate what the power that each resistor is using as it goes around the system. So let's see here. So 0.5 times 3, well, that's going to be 1.5. 0.5 times 4, that's going to be 2. 0.5 times 5, that's going to be 2.5. And if I'm very, very good, all of the voltages, all of the potential differences as it drops across resistor A, B, and C is going to end up equaling the total resistance, or rather the total voltage, the total potential difference of the circuit, and that's going to be 6. So 1.5 plus 2.5, that's going to be 4, plus another 2, that's going to equal 6, and life is grand. Everything ends up matching up. So what we can see here is when filling in one of these circuit Sudoku tables, all of the resistors, when we're dealing with series, since all of those add up, we end up with 12. And then all the voltages will also then add up, and we're going to get 6. And then the current is the same throughout all because this is a series circuit and the current doesn't have a choice as to which direction to flow. So that's your introduction into how to solve these series circuits. And that will get you started into calculating what the various different resistances, currents, and voltages are in a circuit. And we can go and take a look at the circuit that I made over here. Here we have the circuit, and now we can go and test what those are. So the voltmeter is currently measuring the potential difference across the entire circuit, so both ends of the battery. And we can move those leads to be showing the whole potential difference across those resistors. And you can see it's the same. And now we can move them to see what the potential difference across the first resistor is, and that's 1.5. And we can move these across resistor number 2, and that's going to be 2 volts. And across resistor number 3, and that, just like what we found on the table, is going to be 2.5 volts. With that, I wish you the very best of days.